Good morning, champs. Today we solve our first beam problem with a triangular distributed load. If you watched the previous video, you already know the strategy. First, replace the distributed load with an equivalent force. Then solve the problem using the equilibrium equations. The workflow is exactly the same as before. Consider a simply supported beam with a pin support at A and a roller support at B. The beam carries a triangular distributed load. The load starts at 0 on the left side and increases linearly until it reaches 8 kilonewtons per meter at the right side. The beam length is 6 meters. Our goal is to determine the support reactions. We begin with the free body diagram. The unknown reactions are AX, AY, and BY. Before writing any equilibrium equations, we replace the triangular load with an equivalent force. The magnitude of that force equals the area under the load diagram. Since the load diagram is a triangle, the equivalent force equals 1/2 times the base times the height. Therefore, Fr equals 1/2 times W0 times L. Substituting the values gives 1/2 times 8 times 6, which equals 24 kilonewtons. Now we must determine where this force acts. This is where many students make mistakes. The force does not act at the center. For a triangular load, the equivalent force acts 1/3 of the length from the larger side. Since the larger side is located at support B, the equivalent force acts 2 meters from B. Since the beam is 6 meters long, this is the same as 4 meters from A. Now, the distributed load has been replaced by a single force of 24 kilonewtons acting 4 meters from A. The problem has become an ordinary beam problem. We start with horizontal equilibrium. There are no horizontal loads acting on the beam. Therefore, AX equals 0. Next, we take moments about point A. Solving this equation gives BY equals 16 kilonewtons. Finally, we apply vertical equilibrium. The upward reactions must balance the downward load. Substituting By equals 16 kilonewtons gives Ay equals 8 kilonewtons. The final reactions are Ax equals 0, Ay equals 8 kilonewtons, and By equals 16 kilonewtons. Notice that the reaction at B is larger than the reaction at A. This makes physical sense because the load is concentrated closer to B. The most important lesson is that triangular loads are solved exactly like rectangular loads. The only differences are the magnitude of the equivalent force and its location. Once you know those two rules, the rest is just ordinary statics.